is going to be a formal lab report, and it's going to. These are the old directions. I need to make some modifications to them, but part I'm not mostly going to not modify. This says Bradford assay, which we didn't do, but is this table that's at the end. Okay, and so we're going to go over how to put stuff into this table and this is just in terms of guiding you through the calculations. Calculations are a bit complex, and what we're trying to do is the really big thing from your lab is we're calculating specific activity for your enzyme. And that's essentially how pure your enzyme, it's a measure of how pure your enzyme is. So specific activity is a measure of how pure an enzyme is. Okay, could be something other than enzyme, but it'd have to have something that had some sort of function. So I suppose if you were doing specific activity for hemoglobin, you might see how much oxygen was picked up compared to how much protein you had. So specific activity actually has a more formal definition in terms of an equation. So specific activity is equal to units of enzyme. That's an actual unit called units. Units of enzyme per milligram of protein. All right. Units, what a unit is a unit is a micromole of product made per minute. So what we're going to have is it's micromoles product per minute per milligram of protein. All right, and so I will rewrite this because this is not, that's a little confusing the way it looks, and Outlook is not the best tool for writing equations. So if we're looking at specific activity, okay, and this is the micromoles product per minute is what we're going to be concerned with. So it's going to be micromoles, not molar, micromoles per minute per milligram of protein. You could squash it down if you want, but I'm going to write it like that because this is what a unit is. A unit is a micromole per minute. I want to divide these two up. If we think about your labs, you did a first lab where you measured the activity of enzyme. You collected the data to measure the activity of enzyme. This is your activity. And then in the second lab, you measured how much protein you had. This is the amount of protein. So this is your first lab. This is your second lab. Okay. Questions so far? So milligrams of protein is total protein. It's lactate dehydrogenase. It's actin. It's whatever else chicken breast has in there. Okay, that came through. And remember, you were looking at. We've got a crude sample, right, from the first lab. So now the first lab I'm talking about is the very first lab, not of the two labs for this. You have a desalted sample. And then you have your LDH fraction, which I think for everybody was something either NADH or NADH adjacent. Thank you, Robin. You could ask me to do that too. So what do we expect for the purity of these samples relative to one another? Yeah, Bridget.
We're starting with least pure to most pure.
Least pure to most pure. So we're hoping that this gets more pure. Right? And what that means is that we would have, in terms of our measurements, in terms of this thing called specific activity, we would have greater specific activity. And one way of kind of thinking about this in terms of a picture is this right here. Okay, I like this picture. This one is from a different book, I think, than yours. But so this is perhaps our crude, where red is the lactate dehydrogenase. All right, so we have our crude. It has some lactate dehydrogenase in it, and it has a whole bunch of other proteins as well. You go through your purification and you get your lactate dehydrogenase fraction, and in your lactate dehydrogenase fraction, what do you see? Well, you've got less protein overall, and in terms of the protein you have your lactate dehydrogenase, and it's a much greater fraction of the total protein there. Does that make sense? Okay. Did your total activity of lactate dehydrogenase change from here to here? So total activity, not per protein. It didn't. You've got 5 of these here and 5 of these here. Okay. But per amount of protein, it went up a lot. Does that make sense? That's what the specific activity is about, and that's why we're going to have to calculate it. And what we have to do is we've got a bunch of things that are absorbances, right? Absorbances are absorbances per time, and we need to change those units into micromole and milligrams, okay? So that's what this table is about on the other page. Let's think about this, and we'll start without even bringing the table. I actually tried to put the table here, and it's just too small. A lot of technical problems this morning. You got from the first lab where you had your activity. What do you have? What are your values? What did you do? Do you remember? So what you did is you collected data, right? And so you have time in seconds probably, right? And what do you have over here? You have absorbance. All right, and then you get a graph off of that. And that graph has a slope. Okay? And what's that slope mean equal to? What are the units on the slope?
Yeah.
Absorbance per second, right. You can read them right off the graph. So this slope is equal to some number of absorbance per second. Okay? Well, what we need to do is we need to turn that absorbance into micromoles, right? And we need to turn that seconds into minutes. Agreed? All right, so that's what we have to do for the top part. So let's go ahead and do that. I'm not actually going to do the table if I can help it, but then this is kind of what we're going through, and it'll kind of step by step take you through that. One of these things is easier than the other, right? Let's say my slope was, what were some of your slopes? Anybody remember? 0.0, well, let's see. Some of you had absorbance changes that were like, we wanted to get 0.1, right, over the whole minute.
Mm-hmm.
And so it would be 0.0 something per second. Let's say 0.05 per second.
Mm-hmm.
That sound right? That might be right. That might not be exactly what you guys got. You're probably not more than an order of magnitude off of that. So let's say, pretend our slope is, let's say x is equal to 0.05 absorbance units per second. All right? I want to get that, let's make that seconds into minutes. How do I do that? Seconds to minutes. Okay, we're going to go ahead and we're going to divide by 60, or if we're not sure about whether we divide or multiply, it's easier with time because we've dealt with time all our life, right? But I like to always use my units. So we've got absorbance per second, right? I want to take that seconds that I want to turn into minutes. Well, I know that 60 seconds is equal to 1 minute, right? Okay. So I don't divide. So good. Use your units, right? Keep you from making mistakes. I didn't bring my calculator, so somebody's going to have to help me out with this. Actually, yeah, it's 3 something. Is it 3?
It is 3.
Okay. So we're going to get 3. Well, I'm just going to keep, let's add a significant figure, because don't go through this and have one significant figure. 3.0 absorbance per minute, right? Now I need to turn that absorbance into micromolar. Well, if you look in your lab report, what it says, how do I turn absorbance into a concentration, actually, before I even talk about what's in your lab report? What do I use?
Beer's law.
Beer's law. And Beer's law has what that is different for everything, every single compound at every single wavelength? What? The extinction coefficient, right. The extinction coefficient for NADH is equal to 6,220 molar to the -1, centimeters to the -1. Okay. Actually, you have centimeters in here too. We're just going to ignore the centimeters. Okay, we can do that because the centimeter, everything you did was 1 centimeter. Remember that? So that just all cancels out. We're not going to worry about that. But we know that. So we know that what this tells us is that 6,220 absorbance is equal to 1 molar. Okay, you guys got that? So in other words, you could write this differently, like 620 absorbance. We don't write absorbance because it doesn't have units, but we're going to carry them along here anyway because it should have units because it's confusing otherwise. But so I could put 1 molar on the bottom, but I could just per molar. Are you guys with me? All right, so I can use that as a conversion factor. So now I have.
What if you divide it by the extinction coefficient? The absorbance divided by the extinction coefficient?
I'm going to cancel my units and then I'll know. Okay. Or you could put it into Beer's law. Okay, but so I'm going to do 3.0 absorbance, right, per minute. And then I know that I have 622, I should have had you guys help me with this, is 1 molar, right? You guys with that? Me for that? Absorbance cancels with absorbance. Oh, good, we got rid of it. Okay, but so now I know I've got 3.0. Well, I know 3.0. I need somebody. I can't do this one in my head. 4.8 times 10 to the -4th molar per minute, right? Okay, but I want micromoles, right? So micromoles, not molar. So, well, let's get this over to micromolar, and then we'll worry about the micromoles. Or we'll get it to micromoles. How am I going to get it to micromoles? How many micros in a whatever? A 1. 1 times 10 to the 6. Micro is what, 10 to the 6? So we've got 4.8 times 10 to the -4th molar per minute. And we know that in 1 molar, there is 1 times 10 to the 6th micromolar. All right, we'll go ahead and do that. This I can do in my head. It's going to be 2, right? 4.8 times 10 to the 2 micromolar per minute. Still with me? All right, so now we're almost there. We almost have micromoles. What do I need to go from molar to moles? What am I missing here? Volume, right. So I need to think about the volume. So you did your assay, right? This is the amount of activity you had in your assay. What was the volume of your assay?
Sorry, when I plugged it into Beer's law, I got a different one.
Okay, so we've got to go back.
I did the 3 for the absorbance is equal to
and you had it,
coefficient times
and you divided by 6,220. What did you get? This is just a calculator difference.
It might be.
But go ahead, what'd you get?
It was being weird. I think I just plugged it in wrong because
Okay.
it's close enough. I think I just plugged it in.
Okay.
Actually.
All right, so, but even if the answer is slightly off in terms, if one of us made a calculator error there, the method is still what we're going to follow. All right, so we need the volume. What was the volume of your reaction? 610 microliters. Do you remember that? 300 and 200 and 100 plus 10? Yep. Yes, it was. Okay. So this is why we have notebook quizzes. Anyway, so we've got 4.8 times 10 to the 2 micromolar, right? And now that's going to be micromoles per liter, right? Okay, it looks like I'm going to maybe lose you there. Let's not do it that way. We know that our molarity, right, or our concentration is equal to moles divided by liters, right? So I just need to multiply here. All right. I'm trying to decide. So if it's micromolar. So if this is micromolar, this could also, it would be micromoles per liter, right? Do you agree with that? So I'd be multiplying this times, to make it micro, times a million, times a million. So then we just need to do, what we need to do here is we need to multiply times the volume, right? Okay, so let's go ahead and do that. So if we multiply by the volume here, then we end up with 4.8 times 10 to the 2. We've got micromolar over, which is going to be micromoles over liters. Yep. I'm just, it bothers me to not be able to cancel my units, but micromolar times liters. So we're going to multiply times the liters of what, and that's per minute. And we're going to multiply that times the liters we had, right? So we had 610 microliters, which is the same as 610 times 10 to the negative 6th liters. Okay. You guys okay with that? I did that in my head. Okay. But I can't, what I can't do in my head is the next, I need somebody to multiply 4.8 times 10 to the 2 times 610 times 10 to the negative 6.
610.
610, yes.
It's a really big number.
Okay. It shouldn't be a really big number. It should be a small number.
Oh, it's a negative.
Yep. Let me write that clearer. Okay. It should be like well, it should be something. It's 0.293. Okay. And our units there are micromoles per minute. Questions? So we just got the top. If we think about this, that is, we just did this. All right. Now, there's one thing that we didn't do as we were going along. Let's say that was my activity. And the spreadsheet may have you do this right at the beginning. But this is diluted, right? Because for some of those things, for all of your fractions, I'm pretty sure that you had to do a dilution. I remember kind of everybody had to do some sort of dilution to get their straight line. So for this one, give me a dilution you did in lab. 1 to 10. Let's say 1 to 10, sold. 1 to 10 was your dilution, okay? What that means is my actual activity is what? This was a 1 to 10 dilution, so what was my actual activity in my real sample? It was what? 10 times that, right. Okay, diluted, so that was diluted 1 to 10. And I'll apologize, I think this was done at the beginning of that spreadsheet. So undiluted would be micromoles per minute. Okay. Questions? Okay, so now let's think about, so we got that much activity from a certain amount of protein, right? So you measured how much protein was in one of those fractions when you did your BCA assay, right? You ended up with a standard curve. Your standard curve had absorbance here, and down here it had, I think, micrograms, yes? Micrograms protein. You guys agree? Does anybody agree? I think it was like what? 0 to 2,000 micrograms. So that's what's going to be on the bottom of this axis. So you're going to have some plot here, right? For your protein, you had some absorbance. You can get the line off that curve, right? And then you can use the line to calculate what the X value was for your sample, right? If I have Y is equal to mx plus b, this is my Y as my absorbance, and I solve for my X based on what it's given me in terms of that. Another way to think about that, though, is I can just read this over on my graph, and I can read it down. And that's what my concentration of protein was. All right, so I'm going to let's assume you ended up with 100 micrograms protein in whatever this sample was. Okay, the same sample. Let's say it's your LDH fraction. So I've got 100 micrograms of protein. Let me go ahead and underline those so I get some extra significant figures. And then, so I've got 100 micrograms of protein there. That was in the sample, right, that you measured. How much of that did you add, of that protein, did you add to your activity, your refraction? I'm sorry, how much of that, way back when you did the previous lab, how much of that did you add to that 610? How much of that was enzyme? 10. 10, right? Okay. So you added 10. So that's 600 micrograms of protein in, wasn't micrograms of protein, it's micrograms per milliliter, right? Yeah. So what we need to do is we need to take this micrograms per milliliter, and we have to turn it into how many milligrams would have we had in the 10. And so what you do is you say, okay, I had 100 micrograms per milliliter. Well, actually, let's do it like this. We're going to use that as a conversion factor. So you had 10 microliters protein added. All right. And if I'm going to convert that to milliliters, because this conversion factor here uses milliliters. So if I have 1,000 microliters, I have 1 milliliter, right? Microliters goes away with microliters. And then if I have the hundreds with the microgram on the top, if I have 1 milliliter, I have 100 micrograms. All right, does that make sense? So then I'm going to have milliliters goes away, and now I'm going to have, it's going to tell me how many micrograms of protein I added. Oh, actually, we need to convert that to milligrams. So let's do that, because we need that for the It needs to be milligrams of protein up above. And so if I have 1,000 micrograms, I have 1 milligram. Okay, does that make sense? The goal here is we need to, this is from your second lab, and we need to get what your measurements were in the units that we can put it here.
Okay.
All right, so go ahead, somebody multiply that through for me. There's a bunch of zeros. Actually, it's not all that hard because it's all ones, right?
So is the milligrams of protein, is that our LDH or is that?
This is milligrams total protein.
Oh,
It's all the protein, because that's all you measured with the assay. You didn't measure LDH.
okay.
So actually, I get rid of those. If I can cross out these, and I end up with, it looks like 0.001, 0.001 milligrams of protein. Okay, but did you do dilutions in that lab of your protein? So give me a dilution that you did for which dilution worked for your lactate dehydrogenase? You might have not needed dilute. Let's say it was the desalted. Well, let's say you had to do 1 to 10, okay? Because I want to show what you do with the dilution. So if I did a 1 to 10 dilution to figure out how much protein I was, remember that you did dilutions so that what would have happened in terms of your measurements is you've got this standard curve you've generated, right? And actually, your standard curve probably looked like this, if I remember correctly. Something like that. Actually, not quite that bad. It was like this, wasn't it? Okay. So what you need to do is when we think about your absorbance and we think about your concentrations, you did dilutions because you wanted something that landed here, not up here. Right? You wanted something that landed. The reason why you had to do 3 dilutions is you needed something that landed in the middle of this curve. Does that make sense? Okay, so you're going to pick a dilution that landed in the middle of the curve or didn't land up here, wasn't too high. All right, let's say it was a 1 to 10 dilution. What that means is if this was a 1 to 10 dilution, what was the concentration or what was the amount of protein in the original sample? 0.01, 10 times as much. All right, and so this now goes way up to the top of where we were. Remember way back here? That goes there. Yes?
So to find specific activity for the first part, we used the slope and did all those conversions.
Mm-hmm.
And then for the milligrams of protein, how do you pick which value?
Which of the dilutions?
Or like which value from the graph to use for the milligrams of protein?
So from the graph, it isn't off the graph. You got an absorbent, you have 3 absorbance values, 1 for each of those dilutions. So let's say it's your LDH. You did an undiluted, you did a 1 to 10, and you did a 1 to 100, right? Mm-hmm. One of those is going to land kind of in the middle of this graph, hopefully.
Okay.
It doesn't let me know. But you don't want to pick one of these high ones because at this point we don't know what the concentration is. It's something greater than whatever this would indicate right here, right? But we don't know because it's the graph's curved over. We need the straight line part of the graph.
Okay.
All right, so we've got so we've got 0.1 and what was it? 2.93. Okay. So we just calculated for our stuff below, we have 2.93 micromoles per minute, and then 0.01 milligrams was our protein. And so that's our specific activity. It's going to be 293. And I'll just go with the, well, let's just keep it micromoles per minute per milligram of protein. Does that make sense? Kind of what we were doing there? That's what you're doing for this lab report, the calculation section. I realize that is tough to follow. And so not me, but Dr. Sariski, when she was here, also realized it was hard to follow and made up a table where you're going to be doing those calculations. Okay, so what we have is we have our fraction, we have the volume, we have the unadjusted slope, right? So here she has you doing your dilution adjusted here. So if your slope was 3, no, it was 0.05, right? Your slope was 0.05. Okay, and it was a 1 to 10 dilution. Now it's 0.5, 0.05, 0.5 for a 1 to 10 dilution. Okay, then you're doing the conversions to change it to micromoles per minute as opposed to, so you're going to use the volume here. And there's descriptions about how you will do that. But so it's not doing it exactly in the same way I did. And I don't feel bad about that. I want you to think about what you're doing for these, but I hope that in my going through those calculations, you're accomplishing the same thing, that you see what we're getting at with all these calculations, right? We're getting an total activity, and then we're getting an amount of protein, and then we're putting the two together to make it into a specific activity. Okay? So we have this table. And then there are directions down here also that help you out as well. Okay, the other thing I'm hoping you'll recognize is that it's a little bit gnarly and you might want to start it before the night before. Questions? Okay. Then what we're going to do is move on into talking about kinetics. I want to give you an example of why kinetics would be important. So this is a reaction that's catalyzed by an enzyme called cystathionine beta synthase. Okay, and what this is this is a reaction that's going to help to break down homocysteine. And so in that reaction, we're going to break down homocysteine to alpha ketobutyrate and cysteine. All right, this is important for, you can see it's a way to make cysteine, right, from serine. It's also a way to get rid of homocysteine, which having too much of can be a problem. And so people who have, so that the enzyme here, once again, I'll write it because it's pretty small there, is cystathionine, there we go, cystathionine beta synthetase. All right, well, from here on out, refer to it as CBS. Okay, and there are some diseases associated where this enzyme doesn't work. So there are diseases where CBS is not fully functional. Okay, and so we have some symptoms. Symptoms we get from those diseases, we get skeletal deformities. We get problems with the lens of the eye. All right, we end up with intellectual disabilities. All right, so we got problems with the brain, and then you actually end up with 50% chance of a heart attack by age 30. All right, so you've got this disease, and you're not processing homocysteine correctly, and so you have a very large set of really bad outcomes as a result from that. So they've done studies on that, and what they found is we get another 50% here, that 50% of CVS diseases result from the enzyme not binding vitamin B6 correctly or tightly. Okay, and when we think about vitamin B6, what it's going to be is it's going to be a coenzyme, or you could call it, sometimes it's called a cofactor. It really depends. There's some very specific, field-specific terminology here where it changes. I'm going to call it a coenzyme here. It's like a heme, vitamin B6 is here. Okay, it's not a heme, but it's providing functionality that you don't get from the 20 common amino acids. All right. So some of you are looking to be physicians in the room or work on other types of healthcare. How would you treat this? You did a test and you knew that from genetics that this was one of the cases where the enzyme was not binding vitamin B6 tightly. How would you treat this?
Is the issue caused from the lack of the binding or from an excess of vitamin B6?
The issues are lack of binding of vitamin B6. Make it bind better, okay. So you could do gene therapy. Gene therapy is tough. It always doesn't catch, right? You could replace the enzyme. That's tough. What else could you do? Yeah, mega dose vitamin B6. So what you do in these cases is you mega dose. In these cases, mega dosing. Is that mega dosing? Mega dosing vitamin B6 is the treatment.
But can't you have like too much? And have you just figured out?
You could have too much vitamin B6, and I don't know where the difference is between what level you'd have to mega dose and what level it's toxic, and they could be like that, right? But they actually in this case do mega dose vitamin B6, so it's either below the billion point where it's toxic, or it's just they're like, this is worse than the toxicity from the heart attacks by age 30 and the other things are worse than whatever the toxicity of vitamin B6 is. Yes.
Does it increase all the B complex vitamins or just B6?
In terms of this?
Yeah.
So increase? I mean, what do they do for the treatment?
Yeah, so like I just heard that you need all the vitamin B's to work functionally. So like if they negative B6, you also need to increase.
You need all the vitamin B's to function, but they do different things in their different chemical structures. So this is, I don't know for sure, but this is most likely just megadosing vitamin B6 because vitamin B6 is a specific molecule that fits in the enzyme and helps it carry out its function. Just like the heme is specific. So you could megadose iron if you have. I mean, actually, you have some cases, right, where you will have people take extra iron, right? So definitely for women, you prescribe more iron depending on what's going on than you might for men. Does that make sense? Okay. Iron, of course, is toxic at higher levels too. I think it's the third highest ranking killer of children is iron poisoning. They get into somebody's vitamins or eat something. Okay, other questions about this? So the point here is, wouldn't it be great if we had a way to tell how tightly enzymes bound things, right? Here's a really good, useful way of seeing that. We can see that we have this disorder, and we know it's because it doesn't bind vitamin B6. It's coenzyme tightly. And so out of that, there's a pretty straightforward treatment, which is you just megadose that vitamin B6. So knowing this is really useful. Well, one way we can figure this out is through enzyme kinetics. You could figure out how tightly things bind using enzyme kinetics. So we can say coenzymes and substrates using enzyme kinetics. And that's what we're going to talk about today. And that's what next week, that's not what we're going to do in lab, but that's what we're going to be doing the next 2 weeks in lab after that. So to do that, we need to think about enzyme kinetics. And this is where, this is usually, I don't know that I have enough time at this point. We spent so much time on the lab talking about the lab stuff, which I think is worthwhile. But I don't know if we're going to have time to get through all of this today. It's a kind of long derivation, but we are going to derive it because it's another one of these examples where we come up with this equation and it just comes from making some simple assumptions, and they're not even assumptions. This is what we did, and then, or this is what we think the model is for our system, and then you just do algebra to it, and out pops this equation, okay? So what we're after here is what's called the Michaelis-Menten equation. All right, so we have the Michaelis-Menten equation. This is in terms of enzyme kinetics, if on whatever nasty test you're taking after this class to get into whatever grad school or professional program you want, they ask you one question from biochemistry. They were only allowed one, it would be enzyme kinetics. Okay, so this, in terms of taking things out of this class, this is the most important thing. They're all important, but this is the biggest thing that we would need to know. So the Michaelis-Menten equation looks like this. Okay, so what this says is that we have the rate of reaction, and this is going to be the initial rate. Okay, and that's going to be equal to the max rate of reaction times, this is our substrate concentration. And then down here, what we have is this is the Michaelis constant. Okay, and it is like a dissociation constant. And we are going to treat it just like it's a dissociation constant. If you go out in the field, you're going to want to be careful about that. I called it a dissociation constant in one of my manuscripts, and I had a cranky reviewer get all cranky on me about it. And he's right, but it is different, but we'll just treat it like it's a dissociation constant. And we'll see where we derive it, maybe not today. All right, so this is a great equation. It is an equation where we're doing a reaction. We're trying to figure out how tightly something binds. And we can use that with our dissociation constant here. And what we can do is we can vary our substrate concentrations to figure that out. Okay, so we can vary our substrate concentrations and we can measure our initial rates. And our initial rates are like what you did in your assays. Remember, I cared about straight lines and I cared about small, lower down straight lines. That's the initial rate. And the big thing about our initial rate is that's the rate before these have changed very much. All right, so I'm doing a reaction. I dump in substrate. I know how much substrate I added. And if I catch this reaction at like in the first 5% of the reaction, that's one of the rules that people like to use for it. The first 5% of the reaction, I can just assume those substrate concentrations haven't changed, right? They were 100%, now they're 95% of what I put in. It's the same. Okay? That's what that initial rate's about. And then I can use the Vmax to figure that out. So I could, this is going to produce a curve that looks like this. If I have my substrate concentration down here, and I have my velocity up here, okay, I'm going to get a curve that my initial rate, my initial velocity there, my initial velocity is going to go up and up. Oops, not like that. You know, get a little spike. It's like what happens on some of the bad UV vises. You're going to get a curve that looks like that. Have we seen a curve like that before? When did we see that?
2 weeks ago.
2 weeks ago when we did our binding constants, right? Okay. So I don't remember. Did I put a binding constant question on the test?
Yes.
Yes.
Yeah.
Okay.
Y is equal to L over.
Yeah.
Yeah.
Great. Awesome. Anyway, so so if you look at this, there's some similarities there, right? Y is equal to our ligand concentration over our binding, our dissociation constant plus our ligand concentration. You see how they're sort of similar? Okay. I'm not going to go through the math for it right here. I'm going to think about whether this would be the first year I didn't derive this, if I decide not to derive it on Monday. But I don't know if I can do that. But what was special? So we got another equation. I guess I shouldn't have erased it yet. Let's put it back here. Look, here's our binding constant equation. Without me going over the reasoning up here, but the reasoning is the same. You see, that's pretty much the same, except we got that Vmax thing in there. What was special about this equation and graphs? At half of max bound, I could get my KD out of it. And it's the same thing here. So if this is my max rate, otherwise known as Vmax, okay? Vmax is my max rate, so I'm lining it up here where I think that's going to level off. I can take half my max rate and I can follow it down. This is 1/2 Vmax, and that's my KD down there. Okay, so that's really cool. We're going to use that in lab. All right, but let me show you something cooler, which isn't quite as cool, it isn't quite as useful as it once was, because now we have computers and we can just do these plots and we can just solve for everything, right? Because the computer can solve all the constants. We don't need to draw a straight line, but we're going to do that. Lauren first.
Yeah, it's supposed to be KD or KM.
KM, thank you. See, that's why I got in trouble with that reviewer. They're just the same in my mind, but you're right, it's KM. Was that what you had? Okay, thank you. So let me show you something else that's really cool, though. And it's cool from the, how chemists like to draw everything as straight lines, right? Okay. Which isn't as important as it once was because we have fancy computers now. But remember, our Michaelis-Menten equation looks like this. Oh, there I did it again. I don't usually do this. All right, what I could do is I can divide both sides of that equation into one, right? I can do that. I can divide this into one and that into one. That's going to be equal. And so if I do that, I'm going to end up 1 over V naught. And then if I divide it into 1, I'm just flipping it. Okay, you guys with me for that? All right, and now I can actually separate out the top two terms. So I can do this as Vmax over substrate concentration plus substrate concentration over Vmax over substrate concentration, right? You guys all right with that? Just separate it out, kept my denominators. All right. Now I can cancel those two, right? Okay, and I can rewrite this. I'm going to rewrite this slightly just to make a point. I can take Km over Vmax. Those are actually both constants, times 1 over substrate. That's this rewritten, yeah? Okay, and then I can take 1 over Vmax is what I'm left with after I cancel. Okay, and so this is a constant, right? Let's call it M. Vmax is a constant. This is a constant. Let's call it Y. This is something I vary in my experiment. Let's call it X. And this is something I measure in my experiment. Let's call it Y. Let's call this B. I'm sorry. This is a constant. Let's call it B. And what have I got? The equation for a straight line. And so if I actually was to plot, if I was to vary my substrate concentration and measure my initial rates, and then I plot them as 1 over V naught and 1 over substrate concentration, I'm going to get a straight line, okay? And what's the intercept for that line going to be? 1 over Vmax, so I could figure out what the maximum rate of my enzyme reaction was, right? And if I know what my Vmax is, now I know what my Vmax is, what can I figure out from that? The slope here is going to be equal to my Km over my Vmax. Okay, and so if I can figure out my Vmax from my intercept, then I can come over here and use that, the slope and my Vmax, to figure out what my Km is. And now I figured out how tightly something binds, because it's like a dissociation constant. Questions? Okay, well, I'm going to let you go with that. We'll see if we end up doing a bunch more math on Monday or not.